All right. First, this talk is called PSCache, Simple Strategies for Magnificent Performance. This name, PSCache, is taken from a module that I originally wrote a year and a half ago to kind of write an abstraction around a common problem I had with regards to performance when I was querying Active Directory. I work at a big company. We have a lot of reporting depending on Active Directory, and we had a lot of integration scripts that were running really slow. And so the infrastructure team came to me and said, you know, this PowerShell thing, it's kind of your thing. Can you help us troubleshoot this? And so we worked on this. We got some really massive performance increases with some super simple approaches, really. And after that, I kind of put this very simple module out there. Around 5 months ago, when I submitted this talk for this session, I had just written a plan of what I wanted to do with PSCache because I had some ideas for how we could make this really nice and flexible. And then life got in the way. So I didn't implement any of the things that I planned, as it happens. And so what we're going to do today instead is we're going to do like a gentle introduction to kind of computational performance analysis. We're going to have a look at some examples, some very simple examples of how you can kind of analyze and improve the performance of your scripts. And then at the very end, we're going to take a look at PSCache as it looks right now. And then maybe I'm going to talk a little bit about what I would have done had I had the time. Okay? Right. Before I start, does this resonate with anyone? Right? I saw this on Monday when we just came in here, and I was like, spot on, right? Spot on. The hardest thing about coding is knowing what to Google. And what I usually find when I scour the internet, maybe Stack Overflow or other forums for interesting problems to solve, is that people ask questions like, can you make my code fast? Or, this is slow, please fix. And so there seems to be this kind of misunderstanding that here's some slow code, can you pour some magic sauce over it and it'll become fast, right? And what it seems to me is that a lot of people don't have the foundational understanding of how their computers work, and therefore they can't really kind of make the connection as to what they need to do to their code to make it faster. So we're going to talk a little bit about what terms you could Google to get better at that. First, a little bit about me. My name is Mathias. I work in something called the Threat Detection and Response Team at Booking.com. I like to think of myself as kind of mired in Windows behavior. I've been fascinated with programming computers and Windows as an operating system for most of my life. Privately, I'm obsessed with PowerShell, as some of you might know. I'm kind of addicted to Stack Exchange, Stack Overflow, and so on. If you want to find me on Twitter, GitHub, Reddit, feel free to reach out. I'm always happy to discuss PowerShell. So, what we're going to talk about today, we're going to talk today about the fact that when we use computers, we're bounded by physics. We're going to talk a little bit about how we can get help to solve some of these problems from math. It sounds scary, it's going to be okay. We're going to talk a little bit about basics of PowerShell performance. I have a couple of examples that kind of show how you can get some vastly different results in runtime performance from making very simple changes to your scripts. And then we're going to have a look at some tools that you can employ to analyze your slow code and maybe do something about it. Right. The best way I know of kind of showing that we're bounded by the laws of physics when it comes to computer performance is from a presentation that Jim Gray, technical fellow at Microsoft Research, gave about 20 years ago. And he basically had this analogy of what happens when you try to access memory in your computer. And he came up with this kind of graphical device. Basically, what happens in the CPU register in terms of the time it takes to access and process memory is on the order of nanoseconds, right? If you translate that to how fast your intuition works and then kind of extrapolate from there, using the chip cache, so the level 1 and level 2 CPU cache, would be equivalent of walking across this room. Fetching something from RAM, we tend to think of random access memory as being really fast, right? We'd rather take something from RAM than from disk. But even compared to the CPU register, we're already 100 times slower. I think this lecture was originally given in Los Angeles, and the equivalent would be to walk to Sacramento in order to fetch your memory from RAM. When we start talking about RAM versus disk, it gets even worse. We're talking about millions of nanoseconds before a call to, through the file system driver and down through the bus and back into the CPU actually reaches and you can do anything with it. And this kind of shows the date of this visual, but a tape or an optical robot would be the equivalent of traveling to the Andromeda galaxy and back again. Usually our human brains are not really wired to think in these sort of exponential distances, right? So sometimes I show this to people and they're like, that can't be right, right? The equivalent of traveling to the Andromeda galaxy. But in terms of the relative magnitude, that's actually how slow it is. So please keep this in mind. You might at some point hit a limit as to what you can ask your computer to do, because the electrons over the wire need to travel and they're bounded by the laws of physics, right? Speaking of scary sounds, these are the scary sounding terms that I would ask you to Google either later today or when you get home. If you Google computational runtime complexity, you're going to get a bunch of links to research written by academics, and it might feel a bit overwhelming. But there's also plenty of articles written in kind of human language that people can understand, but they won't ever get to that because they don't Google for things like computational runtime complexity. Another thing that's good to know is this concept of asymptotic analysis. This is where math gets into it. Asymptotology is the study of limiting behavior of mathematical functions. So that is, in the worst or the best case scenario, what kind of behavior can we expect from a function? When we transpose this into computer programming, we can take a look at our algorithms, and asymptotic complexity algorithms basically tells us something about the performance, best and worst case characteristics of the algorithms that we implement. This may sound very foreign, very academic. If you look this up, there's going to be a bunch of mathematical formulas that I don't understand, and maybe you won't either. The basics of it is that you'd want to avoid nested loops, because that's how you get exponential performance decreases in your scripts or in your code. And so one way this is usually expressed is using something called big O notation or asymptotic notation. And big O notation basically tells us something about the relationship of the input to a function, so the size of the input to a function, and the number of computations, right? The number of CPU cycles we need to execute in order to get the desired results from that algorithm. And so usually this is visualized like this. This is a screenshot from a website called bigocheatsheet.com. I'd strongly recommend you kind of bookmark this as kind of a reference point. There are many resources out there that goes more into depth, but like as a quick overview, it's like, if you see a description of a data structure or an algorithm that says, oh, this is O(n) to the power of 2, that sounds pretty good, and then you look it up in the sheet and you can see, no, this is actually pretty bad, right? We want to get out of the red and into the green. Right? So being aware that all of this exists, again, you don't need to be a scholar or have a master's degree in computer science, but just knowing that these resources exist out there and that this is a thing and a field that's been studied for many years might actually help you maybe take something back into your scripting. All right. Now that we have like a foundational understanding of approaching computational performance, let's have a look at some other things we might consider specifically to PowerShell. So, kind of PowerShell Performance 101. PowerShell itself is a library written in C#. C# itself is a language written partly in C#. This may sound a little weird, but written in C# and running on a runtime written in C++. C++ gets translated to some assembly, and assembly gets translated into some CPU instructions that the computer can then execute. This is all very nice. In PowerShell, it's very easy to use, right? There's a bunch of things that are taking care of you, but I think it's important to understand that for every layer of abstraction, kind of in this stack, everything gets a little bit slower, right? we need some CPU cycles to kind of have this abstraction translation from PowerShell down to C#, from C# down to the CLR, from the CLR down to something that the computer can interpret, and so on. And so basically, the overhead of running anything directly against the CPU, this is not really relevant for anything any of us are doing, the performance overhead is going to be extremely slow, right? So anything you can instruct the CPU to do directly, anything that takes advantage of microcode optimizations, for example, is going to be extremely fast. Again, on the order of magnitude of nanoseconds, right? Above that, in Windows, there's this other translation layer of assembly. We have the hardware abstraction layer in Windows. Again, if you start accessing devices directly, you're going to get really fast performance compared to like user mode programs. Again, on top of this, we have stuff like the Win32 APIs. Some of you might have seen me tweet about all the crazy things you can do by calling out using something called pinvoke directly to the APIs in Windows. Again, this is going to be orders of magnitude faster than running something in PowerShell, but of course we lose something as well because we don't get all the nice error handling that's in PowerShell and so on and so on. Again, kind of on top of this, we have compiled.NET code. Kind of in line with this, we have some of the built-in functionality that's in PowerShell, operators, loop constructs, statements, so on. And also compiled commandlets. How many here went to Thomas Rayner's session on Tuesday about writing commandlets in C#? Thomas went, right? Right, so knowing what you learned in that session, you can take that home and you can start doing some advanced stuff. But what you're going to find is that if you apply kind of the same approach to solving your problems in C# that you did maybe in your PowerShell scripts, already there, it's going to be orders of magnitude faster than using the scripting language. Because at the very top, we have script functions. And so all of these script functions are interpreted, right? They're not compiled already. So again, there's many layers of overhead that we kind of need to get through. In terms of the computational complexity of our scripts, what you'd usually find, this is a bit of an oversimplification, is that when we start writing our algorithms or writing our functions, hopefully they'll land somewhere on this kind of diagonal axis in which we don't bloat memory too much, but it also doesn't take too long to execute, right? If you have a script that needs to run every 5 minutes, it kind of sucks if it executes for 55. Your boss is not going to be happy about that. If you find yourself up in this wedge up here, something's wrong, right? So basically what we want to do is we want to kind of move down towards this corner down here where we keep memory pressure low and runtime is as fast as possible. As I said before, as soon as we do that, there are going to be some trade-offs. We're going to lose, again, some of the nice functionality in PowerShell if we go straight into C# and so on. So an example of how this can manifest in scripts came about last year before PSConf EU when Tobias, the organizer, posted this tweet. Here's the challenge. He puts in this set of strings, and then the challenge is basically, can we scramble all the letters in each string so that the first and last remain intact? To kind of show that our human brains are kind of cool, and we'd be able to read it anyways. And so Tobias comes up with this abomination of a regex function. If you can't read this, I think I promised someone earlier that this conference would be a regex-free safe space. I'm very sorry about this. You don't need to be able to understand all of this. But he came up with this solution. And obviously, I jumped in and I said, no, we can probably make this a little more concise. So we ended up with something like this. This is probably even less readable. Again, I apologize. But this got me thinking, because basically what he's asking us to do, or a solution that would satisfy his challenge, would be to take all the characters in a string that's not the first and the last, and then basically reverse them. And so this question popped up in my mind. Okay, what is kind of the simplest, most concise PowerShell function we can write to reverse a string? So what I wanted to show is a kind of pipeline-friendly sort reverse, basically. So basically, we pipe some input to sort reverse, and it all gets out in the reverse order. Fairly simple, right? Bartek, my friend, came up with an initial implementation of this, so his name's in there. But again, you'll see that our names will be sorted in reverse. Right. So let's have a look at that. Here we go. So we came up with 3 implementations of a reverse sorting algorithm, and I would rate these from horrible to not so bad. The first one, as you can see, we specify a variable called rank. We give it the maximum value an integer can hold, and then we take the input and we basically sort it based on decrementing this rank variable from the parent scope. So this is why I do get variable scope 1. I want to call back into that rank variable that we defined in the parent scope. I take that value, I decrement it every time, so that the first object that comes in is going to have the highest value, and therefore sort object is going to reverse the order of them. So if I define this function, you're going to see that sort var reverse. Sure, it works. Okay. Then someone said, well, you could also use a list, and just instead of adding to the list every time, you just insert at the top of the list instead. So we ended up with a function called sort list reverse, and it looks a little bit like this. We create an array list. This could also have been a generic list. We inset at position 0, so we keep kind of pushing objects into the top of the list rather than adding them to the back of it. And then at the end, we just output the list and have the pipeline take care of enumerating that. So again, you can see with our very simple example here, sort list reverse, yep, also works just fine. And then finally, I thought, ooh, there's something else we can do here. This whole inserting things at the top of the list, there's another type of data structure that's actually designed for this kind of thing, which is a stack, right? A stack works by you pushing things down on top of it, and then you kind of pop them from in the same order again. So this is kind of the reverse functionality of a list or a queue in terms of insertion. And so we can do the same thing. We simply create a stack. For every input object, we just push it down in the stack, output the stack, and have the pipeline take care of enumerating it. So again, one through 5, sort stack reverse, and again, functionally correct. Okay, this all seemed to execute pretty fast, right? Like I hit enter and we get the result immediately. This doesn't tell us a lot about the performance characteristics of this. So how can we figure out about that? Can't argue with that. So since PowerShell version 2, we've had this command called measure command. This is kind of a godsend. It's a very simple tool, but basically what you do is you say measure command. Oh, damn it. Do that at the bottom here. Say measure command, and then instead of doing just a list of 5 items that we're going to reverse, we're going to do a list of 1 million items. And so I'm going to materialize this first, 1 million. And then I want to do the same thing for the 2 other functions that we have. So measure command sort list reverse, and finally sort stack reverse. Then we're simply going to select the total amount of milliseconds that this took to execute in total. As you can see now, it's running in the background. This is going to take a little bit of time, primarily because of the first function where we try to access a variable outside the scope. Variable operations, a million times, exactly. Variable operations in PowerShell, and this may be a little bit counterintuitive, but variable operations in PowerShell, because it is an interpreted language, there's no compiler in there to kind of shortcut or cache anything. Variable operations in PowerShell are extremely expensive compared to, say, local variables in a language like C#, for example. I can't remember how much I actually piped into this when I did the test demo at home, so I might have given it a little too much to work with here. So we're going to give it another few seconds and see if we get anything. Yep. So right now, PowerShell is working overtime. All right, we're going to scale our ambitions back a little bit. It's still working. There we go. So we're going to scale our ambitions back a little bit and do just 1,000 items. And here you can see that the first one that we got out was the one where we accessed variables in the parent space, right? And as you can see here, it's actually 10 times slower than using either a list or a stack. So let's amp it up a little bit, say 10,000. Now we're starting to see some difference in performance of the last two as well, lists and stack. The reason we don't really see the same kind of magnitude in the first place is that, again, a lot of things are going on, right? There's a lot of jitter in here. We're not only measuring like stack insertion. There's a bunch of other things going on as well. Pipeline binding, for example, is going to occur 10,000 times in all three examples. So there's like an upfront investment cost that we incur. And so when we start increasing the input size, we're going to see a bigger difference. So let's try with 100,000 items. It should finish within 10 seconds, 15 seconds maybe. So here, we see that even though we amp up the input to 100,000 items, the stack doesn't care. It's just fine. As long as you keep pushing down in the stack, the way it's implemented is that it's optimized for exactly this kind of insertion, and it takes the exact same amount of time every time you push. What we're seeing with the array list is that once in a while, the array list needs to resize. It's backing the data in an array somewhere, and at some point it's going to hit the limit of its capacity, and then kind of in the background, it's going to resize that array. That takes a bunch of CPU cycles. It's going to copy all the data from the existing array into that array, and this happens a couple of times. And as we amp up the input size, this is going to incur some overhead as well. And so this is why we now start seeing detrimental performance from a list as well, even though it seemed like it was kind of fast in the first place, right? So again, when you test these kinds of things, if you're testing processing of files, do not do it against a folder with 2 items and say, oh, it executed within 5 seconds, it's all good. Because when your colleagues deploy this against a folder with 1 million files, it might all of a sudden take forever to run, just like we saw with the variable example here. If you go to bigocheat.com, the website we were looking at before, you're also going to see a table of these performance characteristics. And basically what you're going to see is that for a stack, the time for insertion is always linear. It's always going to be the same, and this is why it's super fast. All right. Another great example of like how some behaviors that we might not think too much about can really affect performance is this is an example I came up with some time ago. This script is called test null performance. And so basically the idea is that we run some code, we have a function, right, and it produces some output that we're not interested in. So we want to get rid of that input. We don't want to use that memory. And so there's a couple of different things we can do in order to suppress output in PowerShell. One that comes to mind, kind of the PowerShell idiomatic way of doing this, is piping to out null, right? We pipe to out null, and the output kind of just vanishes into nothingness. This is a little bit like on Linux, piping to dev null, for example. Let's see here. Another thing we could do is we can take the entire value expression and we can assign it to the null variable. If we do this, it's also just going to disappear because the null value, the null variable is kind of magic. It just takes anything, and as soon as you reference it again, it's null again. Another thing we could do is we can use the file system redirection operators and redirect to the null variable, and this is going to have the exact same effect. And finally, we have two typecasting tricks down here where we can either cast the entire expression to void. Void is nothingness, right? So obviously nothing is going to come out of this casted expression. Or we can do an unchecked cast with the -s operator that was introduced in PowerShell 3.0. So what I'm doing in this script, we could also have used a measure command, but basically what I'm doing is I'm creating a stopwatch. I'm starting that stopwatch. I'm then going to take a number of objects, materialize those, and then do one of these output suppression strategies. And so if we say this, and there's a pretty good example here. What I'm doing here is I'm going to take 4 different input values, or input values of 4 different sizes, 10, 100, 1,000, and 10,000. Oh. And I'm going to pipe that to for each object, and then we're going to run this script with the 5 different output suppression methods and say that it should do X number of iterations, right? So if I do this, it exits pretty fast, right? This didn't really tell us a lot. Although we're actually already at 10,000 objects or 10,000 integers, we're starting to see that piping to out null incurs some overhead, something the other methods doesn't really seem to have. If we kind of amp this up a little bit, say times 10. Oh. Oh yeah. 10 years of PowerShell. Okay, now it's starting to become a little more clear. We're starting to see a little bit of overhead, a little bit of jitter from suppressing output of 100,000 objects with all of them, but out null is really taking off here, right? Like we're down to 1/6 of a second. Again, if we kind of amp it up once more, now we're actually going to have to wait. And again, we see all the other methods, yeah, they're actually kind of fast. I think if you do this in if we did this in PowerShell core, we can try that. We might see some slightly different performance characteristics because as PowerShell gets upgraded, right, we start getting more and more performance improvements into the engine as well. So if I run this here, where am I right now? Down here, you'll see that some massive improvements have been made to out null. namely that when the pipeline processor sees out null at the end of an enclosed pipeline expression, it just says evaluate and don't do anything with the output, right? So what happens in PowerShell 5 before this improvement was introduced is that it would just work like any other commandlet, right? Every single object that's piped through the pipeline has to be bound to some input object parameter on out null, right? And this is where all the overhead comes from. It's all the background noise from piping that gives us these terrible results. And so, you know, someone was looking at this recently and said, you know, we can probably do better, and sure we can. So again, kind of PowerShell performance pro tip number 1. Upgrade to a new version of PowerShell. There's like not a joke, right? Like there's a lot of stuff going on in this space, and this has been the case since version 2. Version 2 to version 3, massive performance improvements from moving from the .NET CLR to the dynamic language runtime. Again, version 4, 5, And then now with the PowerShell core being open sourced and kind of more eyes looking at the code, we're starting to see some of these massive performance improvements. So again, especially if you're using PowerShell core, make sure you're on the latest version if you want to reap some of these benefits. Right. Okay. So as I said before, I want to talk a little bit about kind of the approaches and tools that you can employ, super simple, to both analyze and maybe improve the performance of your scripts. Basically, number one, I would say, learn how to express your algorithms in pseudocode. And what does this mean? This basically means learn to write down in Notepad or VS Code or on a piece of paper the algorithm that you want to introduce without all the syntactical sugar that you need when you actually write code, right? And so a good example of this is here. Optimize Word document keyword search. I stumbled over this question back in 2015, and what the asker was doing, he had a large range of Word documents. He had a set of keywords, and he needed to figure out which of these documents contained one or more of these keywords. And so he drops in this massive blob of code and basically says, make it faster. Okay. So I thought, okay, this may be a great, an excellent opportunity to educate on how we can approach this problem. So basically I said, okay, let's try to simplify what you're doing right now. Take all of the COM object and word-specific stuff out of there. Just write down with something that looks like code, but are really just English, what are we actually doing? So if I take his current code up here and kind of transcribe that into sort of pseudocode, is what we do is, for each keyword, we create a new instance of the Word application. Oh yeah, for sure. Sorry about that. Is this better? Right. So for each of the keywords that he needs to search for in his documents, he's going to create a new instance of Word, the application, and then for each file, he's going to load that Word document, and then he's going to attempt to find the keyword using the API. And so, as I pointed out, this is where we come back to this asymptotic complexity analysis, right? This basically means that if you have 100 keywords, and you have 10 documents through which you want to search, you're opening 100 instances of Word. I don't know how many people here have used Word, but once you've launched the application, you can open multiple documents. You don't need to launch a new instance of Word.exe. So basically I said, well, if you flip this on your head, the most costly operation here is instrumenting the COM service to spin up a Word application in the background. So if we can limit that to just once, then that's overhead we only need to incur once, right? So basically, take the pseudocode, we rewrite that, we say we create one Word application, shaves off a bunch of overhead, and then for each file, because this is the second biggest overhead we need to incur, actually loading the file from disk into Word, having it pass it, we're going to load that document once, and then for each keyword, this is already memory, he has an array of strings or something like that, we're going to go through the entire document and search for each keyword. And so I thought, okay, what else can we do? Since this is a Word document, and Word since 2007, I think, is based on an OpenXML standard, what we can also do is we could also just take an OpenXML parsing library, pass the entire document, and then use that to search through the document. Because the OpenXML library has a function to basically flatten all the text in your document, and now you can just search through it with whatever tool you want, with a stream reader, some regex, whatever you want to do. And basically, I can't remember, I tested this, but it was like an order of magnitude of like 20,000 times faster. With the first maybe, the first 1,000 coming from just doing this exercise, writing the pseudocode, looking at what's most expensive and see if we can invert that relationship. And then the last bit kind of coming from not even having to open Word at all, just loading a DLL in and writing from the files directly. So again, become comfortable with just sitting down and describing your code with actually writing it. Like a lot of problems can be solved on a piece of paper before you actually run into these problems with your implemented code, right? All right. Other than that, we've already looked at measure command, very simple tool, executes a block and tells us how long that took. If we want to get a little more sophisticated, there's a couple of tools out there. One I want to highlight is a tool called Chronometer by Kevin Marquette. And another one is something called Measure Script. This was originally a sample application in the PowerShell 3.0 SDK. The program in the sample application was a little bit broken, and someone took this and ported it to PowerShell when PowerShell introduced classes in version 5. This was also a little broken, so I took it and I fixed it. And basically what these two scripts do is they will do the same thing as measure command, but for each individual line, they're going to try and measure how many times it executed and how slow it was. So we're going to have a look at Kevin's module Chronometer here. And basically the idea is that you say get a chronometer, you give it a path to a script. We can use our, let me just see here. Use our array reversal example from before. I'm just going to crank the input size down to 10K again so we don't have to wait forever. No, it's the right script. Do you know why this is, Kevin?
I think as a parameter command you can run, which would be the same script. But like list the files I want to parse versus the command I want to run. So I do like cache
Script one.
and then call your script again inside that.
Ah, okay. So again, this is going to execute the script. As you can see, the warning that I got before, it says here, passing files did not result in any breakpoints. Breakpoints, why is this? So the reason is that the way this tool is implemented is by passing the input file and then adding a bunch of breakpoints, because as soon as you get the debugger to break, you can then make your measurement, how long did this line take to execute versus the last one. But this does not seem to work as intended. Ah, here. So I'll put that to the format chronometer, should be right. All right, much better. So the cool thing about this tool, and why I wanted to show this, is because of this format chronometer thing. And basically what that's going to tell us is who's the sinner in this script? Why is this so slow, right? And so as you can see here, it has some measurements for how long it took to execute in total, and the average time based on the number of executions. And basically what we can see here is that this is way slower than anything else. And again, this is because we're calling out to get variable. Had I broken this into like multiple statements so that it would be on a line of its own, this would definitely come out as kind of the red one. The other tool I was talking about, measure script, is a little bit different. And I think this is maybe better as kind of a showcase of what you can do with ASTs. Some of you might have gone to Chris Bergmeister's session about PS Script Analyzer yesterday or the day before, or if you saw my talk on Tuesday. This ability to kind of inspect the AST, this intermediate language representation, is super powerful when you want to analyze your scripts or you want to build editor tools or something like that. But what this project kind of showcases is that you can take that a little further and you can start modifying the AST by implementing something called an AST visitor. And this is basically how measure script works. It basically tries to do the exact same thing. It tries to count how many times a certain line executes and how much each execution takes, how much time it takes. But basically, you can see there's a lot of code down here. We're not going to go completely into detail about it, but basically, down here is we take the script as it is in its past form, the AST, and then we inject a stopwatch into the script or into the AST. So that means that when the AST gets passed on to the runtime is going to execute some extra code around the code that we actually passed into it. So we're modifying the code in line after it's been passed. And so again, if you think all of this AST stuff is kind of cool, I'll definitely recommend you have a look at this module. If you just want to know if your scripts are slow, I would definitely go with Kevin's because you can see it puts out way nicer formatted output. Right. Finally, at the end, as I said, this talk is called PSCache. And so obviously, I can't leave without talking about PSCache a little bit. Basically, a cache is, as we can see in definition 3 down here, a computer memory with very short access time used for storage of frequently or recently used instructions or data. So the idea is here, if you remember the storage latency slide from before, there's a bunch of overhead when we need to access the disk, or we need to wait for a network call, or you need to call out to the internet, or query Active Directory, or something like that. And so if we're querying the same data over and over again, or multiple times, maybe it makes sense to hold a local copy of that data in memory, and then we can access it again without waiting for the query to complete again, because, I mean, we've already looked it up, right? So the original motivation for this was one of my colleagues came with me with a script. He needs to do some reporting. We have a large customer service department, and we have these call center agents. There's a lot of them, thousands of them in Active Directory. They're all in different teams, they have managers, and we need some sort of report on the organizational hierarchy from Active Directory. If you look at the code up here, you might spot a couple of things that are kind of off. Is anyone here familiar with the Active Directory module or work frequently with Active Directory? Right, so there's a couple of people here. Basically, in the first one, get AD user filter, okay, we're filtering on only the people who have agent in their titles, but we take all the properties back from Active Directory. This means that the Active Directory domain controller is going to have to fetch all the data from its database that it might not have in its cache, because there's also a caching layer in Active Directory. It needs to send all of that data over the wire. If you're on a slow connection, that's going to incur more overhead time that you're waiting for it, right? And then finally, we take the data down here, and then we need to find the name of the manager. The manager attribute in Active Directory holds a distinguished name object to another user. And so we can't really use that. It's not a very nicely formatted form of the manager's name. So down here again, we just call get AD user one more time, with the identity of the object being the manager attribute down here. Okay, so I said, okay, first of all, let's just take the manager property, because that's really the only thing we need other than the name, right? No need of getting a bunch of dates back that we're not gonna use. And so I thought, okay, instead of doing all of these individual calls to get AD user, maybe we can maybe we can cheat a little bit and request some of the data up front. So what I do is all users get AD user filter star. So I just get all the users. The default attribute set will include the name, which is what I want. And so now I can loop through all the original agents, and I can do manager all users where the distinguished name is the same as the value I have from the agent, right? The problem with this, and this may not be obvious, is that I've just created a nested loop, and I've now created an exponentially terrible searching algorithm. The reason this is not obvious is that there's not really any loop construct, but as soon as I do .where, that means that it needs to take that entire collection and loop over it in the background. So even though you're not doing a for loop or a for each loop, PowerShell is still doing a nested loop in the background. And I think this kind of catches a bunch of people off guard. Like, oh, I just piped to where object, or I used the dot for each object. It's like, it's still a nested loop, and it's still going to be extremely slow. And so what I did instead is I wanted to see if I could abstract this away with a PowerShell class. And so I came up with this, this class called the PSCache. And basically what we're doing here, instead of using an array to hold all the data, is we create a dictionary. So a hash table, you can see down here. Basically we create a hash table that we're going to use as a lookup table. We pass a script block into this class, which is going to be our fetcher. This is basically the code that's going to execute every time you want to query the backend store for this cache. And then basically, when you want to get an item out of your cache, we just check, does our hash table already contain? And again, if we went back to big old cheat sheet, we're going to see that the search time for a hash table is linear. It's going to be extremely fast no matter what we search for in there. And so this operation is extremely cheap. If it's already there, fine. We just return the cached item that we already have. If not, what we're going to do is we're going to execute this fetcher block, this script block, and then we're going to add that to the lookup table and then return it at the same time. So with this model, worst case scenario, we don't have the user in the cache already, and we're going to make the same call to get a user, for example, that we already did. Best case, we already have a copy of that data, and therefore we don't need to query it again. And so in the scenario before, where we have maybe a team of 20 agents with the same manager, I can now cut the number of calls back to Active Directory by magnitude of 20. Right? I think I'm kind of out of time. I would have loved to go a little bit more into what we can do with the PSCache, but that'll have to be for another time. Thank you very much.